Okay, good. I just see some verbs. Is it recorded? Okay. Yeah, so it's my pleasure to announce today's talk. Our second year MSc student, Sohini Mukherjere, will talk about the homological approach to the Jordan separation theory. And it's a nice topic because it connects with many things. Connects with multivariate calculus, and also algebraic topology, and complex analysis. So the Jordan separation theory is a generalization of the Jordan curve theorem, which is important in complex analysis.
Okay, so good evening everyone. So motivating by a real life example, why is a house necessary? House is a basic necessity for everyone because the walls of a house creates a bounded environment for us which separates us from the outside world. Hence, illustrating this mathematically, we can do this with the help of the Jordan-Brouwer separation theorem, which says if we have a simple closed curve, this is the Jordan curve theorem actually, this is a special case of that one. It separates the plane into two parts, the interior region and the exterior region, the one which is bounded and the other unbounded. Okay, so for that, we need some assumptions from multilinear algebra, which we don't have the time to elaborate here, but we only need some properties for which we'll assume those. So firstly, we assume the existence of a graded R algebra, which we denote by omega star Rn, and we set this to be the direct sum of omega wedge k Rn. Yes, where wedge k Rn, by that we mean that wedge 0 Rn is defined to be simply R, and wedge 1 Rn is assumed to have basis dx1 up to dxn, where dxi corresponds to the ith projection on Rn. Okay. Now, this graded R algebra has a multiplication which is anti-commutative, and that is, by that I mean, if omega 1 wedge omega 2 is minus 1 to the power kl omega 2 wedge omega 1, where omega 1 is a wedge is from wedge k Rn and omega 2 is from wedge L Rn. Now, this space wedge k Rn is assumed to have basis dx1 up to dxi1, wedge dxin, where i1 to ik is wedge k Rn, yes, where i1 to ik is a strictly increasing sequence of numbers ranging from 1 to n. Thus, it has dimension nck. And if k greater than n, then wedge k Rn is simply 0. This anti-commutative graded algebra is referred to as the exterior algebra on Rn. Now, we will define a differential P form on an open subset U. Okay, so from now on, whenever I refer to U, V or U1, U2, these are basic open subsets of Euclidean spaces simply. So a differential form, a differential P form on U is a smooth map omega from U to wedge Prn, and wedge Prn is basically identified with RNCP. Because of that, we can talk about the smoothness of omega. And the space of all such differential P forms will be the vector. It forms a vector space under pointwise addition and pointwise scalar multiplication, and it will be denoted by omega Pu. Now, on this omega Pu, we have an operator which is d from omega Pu to omega P plus 1 u, where for any zero form f, it simply is df is summation del f del xi dxi, where f is a zero form. And for any p form omega, we can write omega as summation fi dxi, whereby dxi I mean dxi1 wedge up to dxi p, because those are the basis elements, so we can write any arbitrary span of that. So for that, d omega is defined as summation d fi dxi. Okay, so this operator d is called the exterior derivative. This exterior derivative has three very important properties. Wait, I'll use that side. Okay, the first one is the one which we have already used in the definition, that for a zero form, df is summation del f del xi dxi, where f is a zero form only. The second property is d square is 0, which is denoted as d compose d equals to 0, and we say it d square. And the third property is d of is distributes over the wedge product, that omega 1 wedge omega 2 is d omega 1 wedge omega 2 plus minus 1 to the power p omega 1 wedge d omega 2, where p is the degree of omega 1, that is omega 1 is the wedge p form, and omega 2 is something from wedge q form that is not needed here. Now, here just an additional but interesting observation which will help you to connect it with multivariable calculus is that when u is an open subset of R3, we have these following observations, that the exterior derivative of zero forms is simply, that is already written, when f is a zero form, the exterior derivative is del f del xi dxi. So see, it is an analog of gradient, which we already knew from multivariable calculus. Similarly, when f is a one form, the df, the exterior derivative of f, gives the formula df2 dx1 del f1 del x2 dx1 dx2 plus del f3 del x2 minus del f2 del x3 dx2 dx3, and the third term is del f1 del x3 minus del f3 del x1 dx3 dx1. Observe that this is the analog of curl, which we knew from multivariable calculus, and when f is omega 2 form, then we have the derivative of f to be del f1 del x1 plus del f2 del x2 plus del f3 del x3 dx1 dx2 dx3, and this is the analog of divergence. Okay, so this was just to connect it with some multivariable calculus which we knew. Now, from the second property, which will be the most important to us right now, that d square is 0, we get the following things. So d square equals to 0 gives, from that we get a cochain complex, which we denote as this, omega p minus 1u, so omega pu, omega p plus 1u, and it goes on like this. So this is the dp minus 1 map, this is the dp map, and by a cochain complex I mean just like I have denoted here, it is a sequence of vector spaces and linear maps between them. where the composition of two consecutive maps is 0. So here as d square equals to 0, so we get dp composed dp minus 1 equals to 0 for all p. And this is the cochain complex. Now an immediate observation from that is that image of dp minus 1 is contained in the kernel of dp, that is because d square is 0. So this quotient vector space called dp mod mdp minus 1 makes sense, and this is denoted by hpu, and it is called the pth Rham cohomology vector space of U. Okay, and the elements of curl dp are called closed p forms, and the elements of mdp minus 1 are called exact p forms. Now, okay, and hpu is defined to be 0 when p less than 0, and H0pu is simply kernel of D0. Now, one can observe that HPU has a functorial structure, and we will explain what we mean by that.
What is the definition of D? And in general, it is not 0 quotient. So there is to be some definition of D.
Yeah, that is from multilinear algebra, which we have assumed. We have assumed the existence of that exterior derivative, as I declared in the beginning.
Should be definition.
Yeah, that is what I defined inductively, and it's the 0 form, that is df is defined by summation del of del xi dxi. What?
If it's not a 0 form.
Yeah, for that omega is expressed in the summation fi dxi, and for that d omega is defined to be summation dfi dxi. That is how I am defining it inductively. That is more general. Yeah. Okay. Now we can observe that HPU has a functorial structure, and for that, if phi is a smooth map from U1 to U2, we have an operator phi star from omega PU2 to omega PU1, where again we will define it inductively like we did there, that phi star of a 0 form f is simply f compose phi, and for any omega, where omega is summation fi dxi, phi star of that is summation fi compose phi d phi I. Yes, okay. So now phi star has 4 important properties, and one is phi star distributes over the wedge product, phi star of omega wedge tau is phi star omega wedge phi star tau. Second is phi star of d omega is d phi star omega. Third is phi compose phi star is phi star compose phi star. And fourth is identity of U star is identity of omega pu. The third and fourth properties are it will make it a contravariant functor. These are known as functorial properties, which I'll explain later. From now, the second property gives us something interesting. The fact that phi star commutes with D makes it a cochain map between two cochain complexes. By that I mean this one. Oh my god. Okay, this is a map. Goes on like this. Omega p minus 1 u1 to omega pu1. These are the maps D, the dp minus 1, dp, so on. These are the And these are the cochain maps between them given by phi star. So basically this diagram commutes. So phi star d omega, that is this map, is same as d phi star omega, that is this map. Hence this map commutes and it gives a cochain map between two cochain complexes. And from this property, phi star induces a linear map at the Rham cohomology level, which will again denote by phi star. So thus, HPU with this associated mass phi star forms a contravariant functor from the category of open subsets of Euclidean spaces with smooth maps to the category of vector spaces with linear maps. Okay, now we are done with this thing. Now we'll use a theorem which says that if X0 epsilon are two smooth maps which are homotopic, here by homotopic I mean the usual continuous homotopy, then there exists a smooth homotopy between them. So using that, we get that if Fg are two smooth maps from U to V, so U, V are open subsets of Euclidean spaces, where Fg are homotopic, then at the Rham cohomology level, we have F star equals to G star. This property of the Rham cohomology is known as homotopy invariance. And we will extend this from the space of smooth maps to the space of continuous maps by a theorem known as the smooth approximation theorem. This says that any continuous map from U to V is homotopic to a smooth map from U to V. Thus, if phi is a continuous map from U to V, we always get a smooth map F from U to V such that phi is homotopic to F. Then we define phi star by setting phi star equals to F star. Now, since we know that homotopy is an equivalence relation, hence the definition of F star is independent of the choice of F. So, by setting now phi star equals to F star, if we similarly have two continuous maps phi 0, phi 1 from U to V that are homotopic, then by the transitivity of homotopy, because both of them are equals to F star, hence we get phi star equals to F, phi 0 star equals to phi 1 star again at the level of Rham cohomology. So the same result holds in the space of continuous maps as well. So this homotopy invariance, we can generalize that in a broader sense to by saying that it holds for continuous maps phi 0, phi 1, 2. This homotopy invariance of Rham cohomology makes it a homotopy invariant functor, which helps us to distinguish spaces up to homotopy, and which is a very important thing, and one of the very important applications of that is that Rn and Rm can never be homeomorphic if n not equals to m. And we will see a different proof of that result by the end of this talk. Okay. Now we'll need some more properties of Rham cohomology needed for our main proof. One of them is the zeroth cohomology group of U is the direct sum of R, m many copies of R, where m is the number of connected components of U. This follows from basic multivariable calculus. And now we finally come to a very important step of our proof, which is the existence of a long exact sequence known as the Meier-Vittorius sequence, which helps us to compute the cohomologies of U1 union U2 in terms of the cohomologies of U1, U2 and U1 intersection U2. So the Meier-Vittorius sequence is the following long exact sequence HPU. Okay, and by U I mean U1 union U2, HPU1 direct sum HPU2, HPU1 intersection U2, then HP plus 1 U And it goes on like this, where this map is called I star, this is J star, and this is del star. Where this del star comes from an application of snake lemma on a short exact sequence of chain complexes, which is available of forms where we have omega pu, omega p, u1 direction omega pu2, omega p, u1 intersection u2 to 0, where this map is I, this map is J, and Ij are basically just inclusion-induced maps. By the inclusion, I mean the inclusion of u1, u2, and u1 union u2, and the J comes from the inclusion of u1 intersection u2 and u1 and u2 respectively. Now, as an application of the Mukherjere sequence, we have this very important theorem which we'll use as an inductive process shortly. Okay, and here we are considering Rn as a subset of Rn plus 1 as the usual canonical embedding, where the last coordinate is considered to be 0. So here, for any arbitrary closed subset A of Rn, and it is proper, we have the following isomorphisms. The p plus 1th cohomology group of Rn plus 1 minus A is isomorphic to the pth cohomology group of Rn minus A for all p greater than equals to 1. The first Rham cohomology group of Rn plus 1 minus A is isomorphic to the quotient of the 0th cohomology group of Rn minus A by R dot 1, wherever R dot 1 I mean the one-dimensional subspace consisting of constant functions, and the 0th cohomology group of Rn plus 1 minus A simply isomorphic to R. So now we are finally in a good shape to proceed in our proof of the Jordan-Brouwer separation theorem. So I'll finally state what it is formally. So it says that if sigma subset of Rn, where we are assuming n greater than equals to 2, is homeomorphic to the unit sphere Sn minus 1, then we have these 3 points that Rn minus sigma has precisely 2 connected components. Say u1 and u2. The second one says one of them is bounded, say u1, and the other is unbounded. And the third property says that sigma is precisely the set of all boundary points for u1 as well as u2. Okay. So now, from the statement, we can see the first part says that Rn minus sigma is precisely 2 connected components. Here, if we simply take sigma to be Sn minus 1, the proof just follows from the direct geometric visualization. Hence, because sigma is homeomorphic to Sn minus 1, so we'll try to use some Rham cohomological tools so that we can somehow replace sigma by Sn minus 1 and get the result to hold for sigma as well. And we actually do have a tool like that, which is the 0th homology space, which counts the number of connected components, because we saw H0u was the real sum of m many copies of R, where m is the number of connected components. Hence, if we can show that for 2 closed subsets AB of Rn, the zeroth homology groups of Rn minus A and Rn minus B are same, and by same I mean apply isomorphism, then we will be done for the first statement of the result. So for that we have these two theorems. The first one says that if A, B are two closed subsets of Rn and Rm respectively, and A, B are homeomorphic by a homeomorphism say phi. Then we have a homeomorphism F from Rn plus M to itself, which is given by x here, comma 0n equals to 0n comma phi x. The 0m and 0n, I mean the m0 tuple and the nh0 tuple. And using that, taking m equals to n, we simply have if A, B are two closed subsets of Rn, which are homeomorphic, then we can, and the homeomorphism is phi. Then we have a homeomorphism phi tilde from R2n to R2n. So now we can see that if we restrict phi tilde on R2n minus A, we get R2n minus A is homeomorphic to R2n minus B, because A is mapped to B by this homeomorphism. And since the Rham cohomology is a functor, which and functors take equivalences to equivalences from one category to another, so we have the Rham cohomology of R2n minus A to be isomorphic to the Rham cohomology of R2n minus B. So now, using the theorem, okay, I rubbed it out, but whatever. We'll only do it for the 0th one, and we can similarly do it for p greater than equals to 0, but we are not doing it here. The same exact proof follows, where if A, B are two proper closed subsets of Rn, which are closed, and they are homeomorphic, then we have H0 Rn minus A isomorphic to H0 Rn minus B. So this follows from the fact that H0 Rn minus A mod R dot 1 is isomorphic to Hn R 2n minus A, that is by the inductive result we wrote, and applying induction by putting m equals to n, we get this following isomorphism. So this is now isomorphic to Hn R2n minus B, which is from this previous one, and this is isomorphic to yes, and this is H0 Rn minus B mod R dot 1. Hence from that we simply have H0 Rn minus A is isomorphic to H0 Rn minus B. Since if they're infinite dimensional, they're isomorphic, and if they're finite dimensional, then subtracting one from their dimensions, we get these two are still isomorphic. Now, we have a stronger result from this, which says that if A, B are two closed subsets of Rn, now in this case, they may not be proper, which is important here. Then the same result still holds, and we get the equality of the number of connected complements. So it says that if A, B are two closed subsets of Rn, which may not be proper here, and they are homeomorphic, then Rn minus A and Rn minus B have the same number of connected components. Okay, so if A, B are proper subsets of Rn, the result simply follows from what we have already done, because those two zeroth spaces are isomorphic, hence the number of connected components are same. When A, B both are equals to Rn, then Rn minus A and Rn minus B are empty, so there's no point of doing that, it's already done. So the case is when one of them is Rn and the other is not equals to Rn. So without loss of generality, let A be equals to Rn and B not equals to Rn. Now we want to use that result, so we are embedding Rn in Rn plus 1 because then A is not equals to Rn plus 1, so we get it to be a proper subspace of Rn plus 1, hence we can use that previous result. So embedding it in Rn plus 1, we see that Rn plus 1 minus A has precisely two connected components, which are namely the open upper half space and the lower half space. So this has two connected components, which we can do mathematically obviously, and this Rn plus 1 minus B is connected, hence it has one connected component. This can be proved directly, but also you can visualize it by the open half spaces. Since the whole Rn is not removed, so there is an intersection point, and we can connect two paths by gluing lemma, and hence prove that it is connected. So since these two have unequal number of connected components, it gives us a contradiction by that result, and this case cannot occur. So we only have that Rn minus A and Rn minus B have the same number of connected components, hence we are done. Now we finally do the proof of the Jordan-Brouwer separation theorem. Okay, so in the first part, since sigma is homeomorphic to Sn minus 1, and sigma is compact, because compactness is a topological property, hence it is closed, so we can apply that theorem to say that Rn minus sigma and Rn minus Sn minus 1 have the same number of connected components. Now Rn minus Sn minus 1 has two connected components, which are the open unit disk and the complement of the closed unit disk. So hence Rn minus Sn minus 1 is exactly two connected components. So we finally get the first part of our theorem. This says Rn minus sigma has two connected components. Now for the proofs of the second and third parts, we'll proceed manually because the boundedness is not a topological property, hence we cannot use the previous Rham cohomology tools we developed till now. So we set R to be the maximum of x varying over sigma norm x. So if Rw is this, by W I meant the complement of the closed unit disk. So basically if it is x in Rn such that norm x greater than R. So this is a subset of Rn minus sigma. This comes from the choice of our R. And now Rw is clearly connected because this is the complement of the closed unit, not a unit disk, but it is R disk. So Rn minus Rw has to be inside R either U1 or U2. This comes from the first part of our proof because these two are the connected components of Rn minus sigma. So if we consider Rw to be contained inside U2, then Rw is clearly unbounded. So we get U2 to be unbounded, and hence we get that U1 is bounded. this proves the second part of our theorem, and for the third part, we have a pictorial proof, which we do as follows. Now, we take a point P from sigma and we want to show that P is a boundary point of both U1 and U2. So, if we consider an open neighborhood V of P in Rn, we will show that it contains points from both U1 and U2. Now, now we take this set A to be sigma minus sigma intersection V. So this is a closed subset in sigma and it's also proper. So by the homeomorphism of sigma and Sn minus 1, it is clear that A will be homeomorphic to a proper closed subset B of Sn minus 1, and Rn minus B is clearly connected, as we can see from a diagram. If sigma is this whole thing, the homeomorphic image, that is Sn minus 1, and if we remove an open set V, we get sigma minus sigma intersection V to be this part, hence it is connected. So, by the result we developed, we get that Rn minus A is also connected. Similarly, because A, B are homeomorphic. So, being open as well, and open subsets of Rn which are connected are path connected, Rn minus A is path connected. So, if we take a point P1 in U1 and P2 in U2, we get a path gamma from close 0, 1 to Rn minus sigma, which starts from P1 and ends at P2. Okay, depicting it diagrammatically, if this is our sigma, and here is the point, say P, and this is the open neighborhood V. This is U1, outside it is U2, and P1 is a point in U1, P2 is a point in U2. So gamma is a path which can go like this, and it connects to P2. So now you can clearly see that gamma has to intersect sigma. Otherwise, Rn minus sigma will become path connected. It will contradict our observation which we have obtained. Hence, gamma inverse sigma is non-empty. So, by the diagram we can see that there will be a first point of contact C1 and the last point of contact C2, which we can prove mathematically by gamma inverse sigma is a subset of closed 0, 1, hence it is bounded, so has an infimum and a supremum, which we can name as C1 and C2, and because it is closed, because gamma is continuous and sigma is closed, so gamma is closed, C1, C2 belong to gamma inverse sigma, and C1, C2 will be strictly in open 0, 1, because they can't be 0 and 1, then gamma C1, gamma C2 will be P1 and P2, which are not in sigma, which are in U1 and U2. Hence, now from these first and last points of contact, we get that there will be a T1 and a T2 here, for which gamma T1 belongs to U1 intersection V, and gamma T2 belongs to U2 intersection V. This is by the continuity of gamma and the openness of U1 intersection V and U2 intersection V. Thus we get two desired points in both of these sections, hence we claim that P is a boundary point of both U1 and U2. Thus we get that every point of sigma is a boundary point of U1 and U2, and for the converse part it's simple that if P is a boundary point of U1, then P cannot be in sigma because Rn is the disjoint union of U1, sigma, and U2, and U1, U2 are open, hence P will have to belong to sigma. And similarly, if P is a boundary point of U2, P will belong to sigma. So we have obtained that U1 and sigma is precisely the boundary points of both U1 and U2. Thus, we have completed with the proof of the Jordan-Brouwer separation theorem. And now we have very interesting and important applications of this theorem. One of them is the famous Brouwer's invariance of domain, which states that if U subset of Rn is open and F from U to Rn is an injective continuous map. Yes. Then the image Fu is open in Rn. And F maps U to Fu homeomorphically. Okay, so for this we will observe that proving Fu is open is enough, because the same proof will hold if U is replaced by any open subset W of U. So for every open subset W of U, we get Fw to be open in Rn, hence F is an open map. So we get F to be a homeomorphism from U to Fu, because it's already injective and continuous, and restricting the codomain to Fu makes it bijection, and since the map is open, so the inverse map is continuous, hence we'll already get this F to be a homeomorphism. So the only thing we require is the openness of U to be proved. And for that we consider an arbitrary closed disk D in U around X naught. Now let the boundary of D be denoted by S. So the interior of D is D minus S. Now proving Fd naught is open is enough to show that Fu is open, because we can write Fu as a union of them. So for Fd naught, when n equals to 1, it simply follows from basic real analysis, because F is an injective continuous map from U to R then, and the interior of D naught is simply the open interval x naught minus delta to x naught plus delta, and we know that any injective continuous map is strictly monotone, so it maps intervals to intervals by intermediate value property, hence we get that Fd naught is open. So we are only left to prove for n greater than equals to 2. So for n greater than equals to 2, we basically want to apply the Jordan-Brouwer separation theorem, hence we need this condition. So S is the boundary of D, and we take sigma equals to Fs. Now these both are homeomorphic to Sn minus 1. So sigma being homeomorphic to Sn minus 1, we can apply the Jordan-Brouwer separation theorem to it and claim that Rn minus sigma has two connected components, which are U1 and U2. And say U1 is bounded and U2 is unbounded. Now we have okay. So now for any subset, if for A subset of Rn is homeomorphic to the unit disk Dn, then Rn minus A is connected. Now Fd is homeomorphic to D, which is homeomorphic to the closed unit disk. So from that we get Rn minus Fd is connected. Now Rn minus Fd is disjoint with sigma, because sigma was Fs and D, S is contained in D, so Rn minus Fd and sigma will be disjoint. So being connected, Rn minus Fd has to be contained in either U1 or U2, because the is compact, hence FD is compact because I get the homeomorphism from D to FD. So being compact, it is bounded. So Rn minus FD is unbounded. So Rn minus Fd has to be contained in U2, which was the unbounded one of the two parts. Okay. Now sigma union U1 is Rn minus U2. So this is contained in Fd. From that we get U1 is contained in Fd interior. Now D0 is connected because the interior of the unit this. So for that FD0 is connected because it's a topological property. Hence FD0, which is subset of U1 union U2, has to be contained in U1. So basically we get the reverse inclusion. So from these two we conclude that FD0 is exactly equals to U1, which is open. So we have finally proved that FD0 is open, which we require to prove that Fu is open. Thus we are done with this theorem. So this theorem is actually stated in a different way. This is just a restatement of our statement. And this says that if V subset of Rn, when V has the induced topology of Rn, is homeomorphic to an open subset of Rn, then say U, then V is also open in Rn, which is simply follows from this because V equals to Fu then. Hence we get the famous invariance of domain. From that we get this very important result called dimension invariance, which says that if U subset of Rn, V subset of Rm are both non-empty, then and also if U homeomorphic to V, then we have n equals to m. This follows because if not, say if m less than n, then from our statement of invariance of domain, we get that V is open in Rn, but this cannot happen because V is contained in a proper closed subset of Rn, which is not possible. Hence it's a contradiction. So we get n equals to m. From this we can also conclude that important theorem that Rn and Rm are homeomorphic if and only if n equals to m. So with that we concluded for smooth manifolds, where a smooth manifold is second countable positive of topological space, which is locally Euclidean, and the transition maps are smooth diffeomorphisms. So for a smooth manifold, by that locally Euclidean I mean that there exists some natural number n such that for all p in the manifold M, we have a neighborhood of P which is homeomorphic to an open subset of Rn. So this n has to be well defined. For that we need the dimension invariance, which says that suppose if there exists some P in M such that there exists a neighborhood U1 which is homeomorphic to some open subset of Rn, and U2 which is homeomorphic to some open subset of Rm, then U1 intersection U2 will be homeomorphic to an open subset of Rn, say U2, say U dash, and U1 intersection U2 will be homeomorphic to an open subset of Rm, say U double dash. So U dash and U double dash are homeomorphic themselves. So by the dimension invariance, we get that n equals to m. So this gives us the well-definedness of dimension of a smooth manifold, which is this number n, for which that is locally Euclidean and is contained in Rn. So similarly, it has many interesting properties like that. And by that, I finally end my talk. Thank you everyone.
you very much for a very interesting talk. Are there any questions? I mean, you used some stuff which comes only in the second year, the snake lemma.
Yes,
But this was done.
Yeah, but it's not actually done till now, but it will be done, I guess. Snake lemma is not yet done.
Can you just say what it says?
Snake lemma, okay.
Yeah.
I'll that later. Refer to the book.
I mean, can we just roughly?
Yes, so. Wait. I need the form. No. So the snake lemma says that if we have a cochain complex of short exact sequence of cochain complexes, A star, B star, C star 0, and here the maps are F and G. Then we get a long exact sequence, which we used in the existence of a arbitrary sequence then, which says that the cohomology group HPA, HPB to HP C star, and it then goes on with HP plus 1, A star, and so on. And where these maps are F star, G star, and del star. This is what the specific case of snake lemma is, which we used here.
Alright. So, that will, I mean, is he teaching now algebraic topology? Shall we?
No, it's in the next semester.
Next semester.
Yes.
Okay, so then it comes next semester, then you will see that.
Yeah.
Yeah, any other questions?
Is there any need to use the Rham homology for that? Like,
No.
homology is also one of the same, like
Yeah.
the moving Jordan-Brouwer, the invariance, and even the manifold dimension.
Right, actually there's a thing where we can say that Rham cohomology is similar to the singular cohomology which comes in algebraic topology. Yeah, but this proof actually comes with the easy application of Rham cohomology.
Smoothness, that
Yes.
is the Rham.
Yeah.
I'm not getting that. Like, is there any particular thing that focuses on Rham homology?
No, the main thing which we used is the zeroth cohomology group's calculation of the number of connected components of U.
Singular homology also calculates the same.
Yeah. But maybe like I'm not much acquainted with singular cohomology right now, hence this proof uses Rham cohomology, hence I developed it in this way.
Okay, if not, then let's thank the speaker again for a nice talk. Yeah, and then some students wanted to talk with me after, yeah. Okay, then you can stay here and then we discuss this.